Let me ask you a question. What is the most rebellious substance in the universe? What is the one material that looks at the laws of physics, the nice clean rules that everything else follows, and says, "No, I don't think I will"? You might guess something exotic, some rare element cooked up in the heart of a supernova, some bizarre plasma, or some strange quark matter, but no. The answer is sitting in a glass on your kitchen table right now. It is water, plain, old water, and I want to tell you something that may disturb you. The more I have studied water, the more unsettled I have become. Because water doesn't just bend the rules a little, it shatters them. It does things that by every reasonable expectation of chemistry and physics, it simply should not be able to do. And the fact that it does these impossible things is the only reason you and I are here to talk about it. So by the end of today, I want you to understand something that most people never think about. I want you to see that water is the strangest liquid on the planet, that its weirdness is not some minor footnote in a chemistry textbook. It is the very foundation of life itself. And I want you to understand why. When you really dig into the physics, the explanation is beautiful but deeply unsettling, because it means the universe is balanced on a knife's edge made of hydrogen bonds. Look at something you have seen 1,000 times. You drop an ice cube into a glass of water. What happens? It floats. You have seen this since you were a child. It is so ordinary you don't even think about it. You would never dream of calling it remarkable. But let me tell you, if you showed that to a chemist from another planet, a chemist who had studied every other substance in the universe but had never seen water, that chemist would faint. That person would look at you and say, "That is impossible. Solids do not float in their own liquid. That violates everything I know about matter." And the alien chemist would be absolutely right to be shocked, because here is the rule that virtually everything else in the universe follows. When a liquid freezes and becomes a solid, it gets denser. The molecules slow down. They pack together more tightly. The solid form is heavier than the liquid form per unit volume, and so the solid sinks. Think about it. When you melt iron and pour it into a mold and let it cool, the solid iron sinks to the bottom of any remaining liquid iron. When you freeze alcohol, the solid sinks. Mercury, gold, copper, nitrogen, oxygen, sulfur, you name it, the solid sinks in the liquid. That is the rule. It is one of the most reliable patterns in all of chemistry and physics. Water says, "Not me." When water freezes, it expands. It gets about 9% bigger. Think about what that means. 9% is not a trivial number. It is enough to burst iron pipes. It is enough to crack granite boulders. It is enough to split a sealed glass bottle in your freezer. All of that destructive power comes from the simple fact that water, unlike almost everything else in the universe, gets bigger when it gets cold enough to solidify. And because ice is less dense than liquid water, it floats. Now, I said that sounds like a small curiosity. Let me show you why it is anything but small. Let me show you what would happen if water behaved like a normal, respectable substance. Imagine a lake in winter, a big, deep lake. The air above it is getting colder and colder. The surface of the lake cools down first because it is in contact with the cold air. With a normal liquid, the cold surface layer would become denser than the warmer water below, and it would sink. Warmer water from below would rise up to take its place, and that warmer water would cool too and sink. This is convection. It would keep going, mixing the lake, decooling the whole body of water gradually and uniformly from top to bottom. Eventually, the entire lake would reach the freezing point. And then what? The first ice crystals would form. Being denser than the liquid, they would sink to the bottom. More ice would form at the surface, and it too would sink. The lake would freeze from the bottom up, layer after layer. Every fish, every plant, every tadpole, every bacterium, every microscopic creature in that lake would be embedded in a solid block of ice. Dead, all of them. And in the spring, when the sun came back, the ice at the bottom of the lake would be insulated by the water above it. It would be extraordinarily slow to melt. Some of it might never melt. Year after year, more ice would accumulate at the bottom. The oceans in their shallower regions would suffer the same fate. Over geological time, vast quantities of the planet's water would be locked away in permanent ice at the bottom of every body of water. Life in the water would be impossible. And since life began in the water roughly 3.5 billion years ago, well, there would be no life at all. No fish, no amphibians, no dinosaurs, no mammals, no humans. An empty, frozen, dead world. And it gets worse. Think about what that bottom ice does to the planet's heat balance. Ice is white. It reflects sunlight back into space. Normally, dark ocean water absorbs sunlight and warms up. But if the sea started accumulating ice at the bottom, eventually that ice would build up to the surface. Now you have vast white sheets reflecting sunlight instead of absorbing it. The planet cools further. More ice forms, more reflection, more cooling. It is a runaway feedback loop. Climatologists call it the ice albedo feedback. Without the density anomaly of water, the Earth might have tipped into a permanent deep freeze very early in its history. A snowball planet, white and silent and dead. You might say, well, surely the tropics would stay warm, maybe. But without liquid oceans to moderate the climate, without water's enormous heat capacity acting as a thermal buffer, the temperature swings even near the equator would be savage. And without liquid water to dissolve nutrients and carry them around, the chemistry of life has nothing to work with. No medium, no solvent, no life. So this one anomaly, ice floating, is not just a curiosity. It is arguably the single most important physical property of any substance on Earth. And it comes from water's refusal to obey the rules. But water doesn't stop there with just one act of rebellion. Here is what really happens, and it is so clever it almost seems designed. Water gets denser as you cool it, just like any well-behaved liquid, but only down to 4 degrees Celsius. At 4 degrees, water reaches its maximum density. That is the point where it is heaviest. And then something deeply strange happens. You cool it further from 4 degrees down towards 0. And instead of continuing to contract, water starts to expand. It gets lighter. The colder it gets below 4 degrees, the less dense it becomes. You see what this does? The coldest water, the water that is closest to freezing, is lighter than the water below it. So it stays at the surface. It doesn't sink. The warm, dense water at 4 degrees settles to the bottom and stays there. So the lake freezes from the top down. Oh, not the bottom up. A layer of ice forms on the surface. And here is the beautiful part. Ice is a terrible conductor of heat. That floating lid of ice acts like a blanket, an insulating cap protecting the liquid water beneath from the frigid air above. The deep water stays at roughly 4 degrees. The fish survive. The plants survive. Life goes on beneath the ice, calmly waiting for spring. All because water has this one peculiar rule-breaking property. If you are not amazed by this, I haven't done my job. Now, you might say, all right, that's one weird thing about water, interesting, but maybe it's just a fluke. Oh, but it's not just one thing. The ice floating business is only the first item on a long list of misbehaviors. Let me go through the charges. Let's talk about boiling. Here's a fact that should bother you more than it probably does. Water boils at 100 degrees Celsius. You know that. Everybody knows that. But do you know how absolutely insane that number is? Water is a small molecule. 1 oxygen atom, 2 hydrogen atoms. Its molecular weight is only 18. It's tiny. Now look at oxygen's siblings in the periodic table, group 16. The elements right below oxygen are sulfur, selenium, and tellurium, and each of them forms a compound with hydrogen just like water. According to the laws of physics, as molecules get heavier, they should boil at higher temperatures. That makes perfect sense. Heavier molecules have more electrons. The attraction between them is stronger, so it takes more heat to pull them apart. Based on that trend, scientists predict that water should boil at something like minus 80 degrees Celsius, way below zero. Water should be a gas at room temperature. Instead, water boils at plus 100 degrees Celsius. It is not just off the trend, it is off the planet. The gap between the predicted boiling point and the actual boiling point is 180 degrees. That's not a small error. That's a colossal disagreement between theory and reality. If water boiled where chemistry says it should, there would be no liquid water on the surface of the Earth. No oceans, no rain, no clouds. And you, who are roughly 60% water by mass, certainly wouldn't exist. Something is making water molecules cling to each other with extraordinary, unreasonable tenacity. Something is giving it a terrifying surface tension, the kind that lets redwood trees 100 meters tall pull water from their roots to their topmost needles without any mechanical pumps. So the question that any self-respecting physicist must ask is there one explanation for all of this, or do we need 6 different explanations? This is the beautiful part. There is one single explanation for every one of these strange behaviors, and it's called the hydrogen bond. Imagine a dance hall full of people. In a normal liquid, the dance is casual. People mill around, bump into each other gently, and drift apart. Water is different. In water, everyone is holding hands with 4 other people at all times. You're connected, and the whole room is connected. If someone tries to pull one dancer out of the room, they can't just grab them and go. They have to break 4 handshakes first. And as soon as one handshake breaks, the dancer's free hand grabs someone else's hand immediately. That is why water is so stubborn. But let me take you one level deeper into the quantum realm, because water has quantum secrets. The hydrogen inside that bond is really just a single proton. Classically, this proton should stay put. But quantum mechanics says the proton can make a leap without ever having the energy to go over the barrier. It's called quantum tunneling. In rings of 6 water molecules, all 6 protons can tunnel simultaneously. They swap positions at the same instant in a coordinated quantum dance without ever passing through the space in between. Yet this kind of collective quantum behavior is usually only seen in very exotic systems like superconductors or superfluid helium, the things that win Nobel Prizes. The universe is very economical with its ideas. When it finds a good trick, it uses it over and over in contexts you'd never expect. And here, it uses it in your very glass of water. So, the next time you pick up a glass of water, just pause for a second. Watch the ice cubes floating and clinking against the glass. When you feel the cool of evaporating sweat on a hot day, or watch rain sliding down a window pane, I want you to feel a chill that has nothing to do with the temperature. I want you to feel the strangeness, feel the depth. Because water, the simplest, most familiar, most essential substance you will ever touch, is a defiant rebel against the laws of the universe. We survive, we exist, only because water refused to obey the rules. Every breath you take, every drop of sweat on your brow, is a physical miracle happening in silence. I must confess to you that despite decades of study, water remains the greatest mystery sitting right on our kitchen table. The deepest problems. The most haunting puzzles of nature don't lie in distant black holes or tiny quarks, but are hiding in the most ordinary places. That makes me feel humble, and it should make you suspicious of anyone who claims that all the interesting problems are solved. They are not. Never. An unsolved problem is an invitation to think. And that, I believe, is the greatest gift the universe offers us. So I leave you with one final question to ponder. If this universe didn't have this proud rebel called water, if it were just a well-behaved liquid that shrank when cold and vanished at room temperature, would consciousness have ever emerged for us to stand here and wonder about it? Or would the universe be forever dark, silent, and empty?